In this video, we're going to be looking at the ratio test for section 4. I'm going to make a couple different videos here. I'm going to split this up a little bit just to get some different examples in. So I'm going to do 3 examples of the ratio test in this video, and then I'll do a couple more videos on some other things with some other problems with mixed tests in there, so you can kind of get used to picking out what tests you want to use. Alright, so the ratio test, so it says useful for a series involving factorials or exponentials. So we have the series of a sub n converges if the limit as n approaches infinity of the series to the n plus 1, so we're adding 1 to all the n values, and then we're dividing it by the original series. If the absolute value of that limit is less than 1, then we are converging. If it happens to be greater than 1 or equal to infinity, then we can say it diverges. And then if we get 1, if it's equal to 1, it's inconclusive. We have to move to a different test. So let's take a look here at some examples. So we have n factorial divided by 3 to the n. So what we want to do is look at the limit as n approaches infinity. So we know that we're going to take the n plus 1 term, divide it by the original. Okay, so if we do that, we're actually, let me write that out. Well, we just dealt with this, a situation where we're dividing a fraction by a fraction. We know what happens. So we're going to take the n plus 1 version of the series, and we're going to multiply it by the reciprocal of the original, because we're dividing by it. So we have 3 to the n. Oops, I forgot to plus 1 down here. Over n factorial. Alright, so once we get to here, we can start hopefully canceling some things out. So that's the purpose of doing the ratio test. So it helps us simplify a little bit. So we remember simplifying factorials. This next term of the n plus 1 is going to be n, and then n minus 1, n minus 2. And then we have down here, we have n minus 1, n minus 2. So remember, all of those things cancel. So we're left with just n plus 1 on top. And then 3 to the n divided by 3 to the n plus 1. Well, we should remember that this right here, I'm going to just make a little side note here. 3 to the n plus 1 is 3 to the n times 3 to the 1. Okay, so if we multiply those together, we would end up with this. So we see that the 3 to the n's would cancel out, and we're just going to be left with that 3 on the bottom. So we take the limit of this. So infinity over 3, or we do L'Hopital's and we figure out top's growing faster, we can say that this is infinity. So we can say that this diverges due to the ratio test. Okay, diverges by ratio test. Alright, so we could have, I wanted to show you this just for the purposes of showing you how the ratio test works, but if you took the original and you did the nth term test, so we're taking the limit of just this, we know that the top's going to grow faster than the bottom. We know factorials grow faster than exponentials, so we could have said it diverges due to the nth term test, and you would be done. I just wanted to show you how the ratio test works. So next example, we're going to do the same thing. We're going to take the, we're going to add 1 to all the n values and take the limit. So n approaches infinity, we have 3 to the n plus 2 divided by 4 to the n plus 1 times n plus 1 squared. And then remember, we're going to multiply by, well, we're actually dividing by the original, but we're going to multiply by the reciprocal of the original. So 4 to the n times n squared over 3 to the n plus 1. Okay. So let's think about the 3's first. So we know that this is 3 to the n times 3 times 3, and this is 3 to the n times 3. So we're going to have some stuff canceling out. We're going to be left with a 3 on the top. Okay, so 3 is left on top. Now let's look at the 4's. 4 will be, we'll have a 4 left on the bottom. And then the n squared and the n plus 1 squared. So we have that. All right, we could multiply the bottom out. We could take n plus 1 times n plus 1 and work everything out, but we should see at the end that the first term in the top is 3n squared, and the bottom first term is going to be 4n squared. And we run the limit. So we have n squareds on top and bottom. We just take leading coefficients. So we have 3/4. So 3/4, that is less than 1, so we can say that it converges by ratio test. Okay. All right. So number 3, this is an example of if we were to take and put this into the ratio test. And you can work this out on your own. It's pretty quick to see what's going to happen. Everything's going to cancel in a way to where we're going to have the same powers on the top and the bottom. And we're going to have leading coefficients of 1. So the limit ends up being 1. So the ratio test is inconclusive here. So we'd have to move to something else. And I mean, pretty naturally anyways, you guys are going to probably use the alternating series test because of that -1 to the n. So we can go ahead and do that real quick. So we see that if we were to look at some terms, we would see that it is decreasing. Okay. And if we ran the limit as n approaching infinity of here, I'll just roll through this just to give you some more visual on alternating series test. Okay, so we're running the nth term test on just that part, remember. So plug in infinity, we could do some L'Hopital's, we just know that n is going to grow faster than square root of n. So this is going to end up being 0. So it is decreasing values and the limit is approaching 0. So we can say that this converges by alternating series. I know it wasn't a ratio test example, but I wanted to show you sometimes ratio test is not going to work. So remember, whenever you have the limit is 1, we have to move on to something else. Alright, so that's it for this video. This next example I'm going to do in a separate video by itself because there is a couple things I want to talk about. We need to talk about what this double factorial is all about. And then we're going to move on to some mixed problems, some series with a couple different things going on. So, alright.